All right. Yeah, so very nice to see all of you here. It's a really beautiful location. Thanks a lot to the organizers for all of their work and for inviting me. So today I'll talk a bit about our work over the past 5 years or so in efficient algorithms for machine learning. So I have some good news and I have some bad news. The good news is that I hope I'll show you sort of exciting stuff that's fairly modern and fairly recent. On the other hand, I'll also need to teach you sort of the basics of it. So it means we're actually going to have like a handwritten part of the lecture and so on. So in case you came to Paphos to avoid the lectures on a whiteboard, I'm sorry, this is not the lecture for you. But yeah, so hopefully we'll be able to get through that together. The other thing is I'm very happy to take questions as soon as you don't understand something. You notice we're not such a wide audience, so please feel free to interrupt, you raise your arm, and I'm happy to take questions. Okay, so good. So I'll start with a broad introduction to kind of sell you the idea of distributed machine learning or efficient algorithms for machine learning, and then we'll move on and try to understand the basics of it and some fundamentals from optimization and how they kind of intersect with stuff we know about like consistency and atomicity and stuff like that. Good. So basically, I mean, the background for my talk is the fact that there's a lot of interest in machine learning recently, and kind of what I want to, the key message I want to convey today is that distributed computing is key. Like none of the stuff that you hear about these days, like ChatGPT or I don't know, sort of computer vision algorithms that surpass kind of sort of human performance would be achievable without distributed computing. And why do I mean that? Basically, because all of this progress has been sort of pushed by data, and by large amount of data or large data sets. What I mean is sort of the classical one for image classification or for computer vision is ImageNet. It has 1.3 million images, and I'll tell you how long it would take to train a state-of-the-art model on such a data set if you don't use distributed computing. And then the modern ones, such as Google's JFT, has 4 billion images. That's literally 1,000 times larger than, or 4,000 times larger than the academic one, than ImageNet. So therefore, people at Google literally need hundreds, if not thousands, of computing machines in order to train on these data sets. There's just not enough, not a single computing node on Earth which is able to go through this amount of data in any reasonable time. So essentially all of machine learning, modern machine learning, deep learning is distributed in some way. And I'll give you another, another example is essentially speech data sets, which are used for Siri and like to basically understand what we're saying when communicating with computers. These have in the order of 3.5 years for single. Essentially, that's the amount of data that they go over in a single iteration, and they go over this data hundreds, if not thousands, of times. And then, if you look at ChatGPT, this has been this is essentially the whole of the internet cleaned to some extent, and so this literally has billions, if not trillions, of words that need to be sort of processed by the machine, and the machine always tries to guess what the next word is, and so on. So my point is, going over this data on a single computing node is nonsense. Like no one would even begin to try to do this. And the point is that distributed computing is essential for this. And in particular, there's a conflict here because on the one hand, people want to distribute their workload as much as possible. So basically, they want to split their data into small chunks, and then each chunk will be sort of computed on in parallel by a different GPU or TPU or what have you. And then the other point is that these models are very, very large. So, but what I mean by this is that they have millions or billions or even trillions of individual parameters which need to be sort of updated in sync in every iteration. And I'll show you sort of the exact pattern of this in the next slides. But the point would be that you have a very large neural network composed of layers, sort of one after the other. And all of these layers need to, I mean, as the algorithm sees more data, these layers get updated, and then we need to sort of synchronize. And the point would be that communication and synchronization, when you're distributing at this scale over this many parameters becomes very, very expensive. And this is what we're practically going to be talking today about for a few hours. And I mean, we all know that this is happening, like we've seen ChatGPT, or like maybe you've worked with sort of computer vision algorithms. So it's kind of reasonable to ask, like, is this trivial, and has this problem been already solved? And I'll try to show you what happens if you basically don't, if you just try the vanilla solution and don't try to do anything, don't try to do anything fancy in terms of distribution. So this is an experiment I ran a while ago, a couple of years ago. But this was basically taking, I had access to CSCS, which at the time was Europe's top supercomputer. I think now it's lower down the line. It has around 4,000 GPU nodes. And then I wanted to repeat one of the sort of most simple experiment that I had described on the previous slide, which was training this ResNet model on the ImageNet dataset. And if I wanted to run it on a single node on this supercomputing cluster, it would have taken me 19 days. So, which is a lot for a single experiment, as patient as you may be. And therefore, if I were able to use about a quarter of this supercomputer, I should be able to divide the 19 days by 1,000 and obtain something like 25 minutes, which is what should be happening in theory. Okay, so I took the standard solution, which was at the time TensorFlow, and distributed, like essentially spawned a run on a quarter of the supercomputer, and tried to estimate the time. Of course, I didn't burn the entire time to actually do this because the results weren't that good. But I just tried to see, like, in estimation, how long it would actually take me relative to these 19 days. So basically, if you spawn on an increasing number of nodes here, so from 2 to 4 to 8 to 16 up to 64, and you'll see there's no point in going past 64, the estimation for the total runtime on 2 nodes was 9.6 days, which is great because this is almost half of 19 days. Then on 4 nodes, it was 5 days, so it's still parallelizing pretty well. And then at 8 nodes, it was 3.2. So again, there's clearly some overhead here, but it still works out pretty well. 16 already starts looking like you shouldn't be using that much compute because the decrease here is no longer 2x. And the embarrassing thing starts to happen at 32 nodes because at 32 nodes, it took me more time than with 16. And at 64, it actually took about the same as at 8, okay? So does any one of you have some idea why this could happen? Like why this should be happening? Yeah? Yeah. Yes, exactly. At this point, if I split this time into communication and computation, and I will actually focus sort of, I'll actually split this for each for each example. Notice that most of our time is spent in computation time, certainly here and here. However, here it's really getting embarrassing, right? Because there's a very small amount of computation that's going on. It's about 10% of the time for the node is actually computation time. And 90% is actually communication and synchronization overheads, okay? So my point in this example is not to bash the people at CSCS or TensorFlow for that matter, but to show you that this is not a solved problem. You actually have to look a bit deeper into what's actually happening, into the details of the system in order to obtain a scalable solution. Basically, a solution where the running time should actually go towards these 25 minutes that we should obtain in theory if we were to use a supercomputer. And my point is a lot of distributed machine learning these days has partially solved this problem. And I'll show you some of the ways in which this has been solved, okay? So this was just to show that this is kind of a non-trivial challenge if you take something off the shelf and start running it, okay? Yeah?
So when you have a lot of nodes, don't you have to move data around?
No, in this case, the way CSCS works is that they have a massive replicated storage, which is this scratch space, which is basically like a fairly complex. Yeah, so you can assume that the reading time for the data is negligible. I actually checked for this, which is why you don't see any data reading time here. Yeah, so then basically they have, essentially each node has flash, and basically there's some kind of replication going on. Yeah, that's a good point. All right, so good. So in order to understand where these overheads are coming from. Yes, of course.
Sorry. So when you go to the GPUs, okay, so the GPUs are kind of naive cores, right? You cannot do everything with GPUs.
Yes.
So what is the part that you can easily parallelize, and what is the part that is difficult to parallelize?
I mean, well, I will discuss this a bit later on, but basically what happens is that you can just assume that every node has, I mean, we have 1.3 million images. And basically what happens is that if we have 2 GPUs, each GPU will get half of that, like about 600,000. And then if we have 4, then each one will get 300,000 and so on. So basically each node, it's data parallel. It's kind of completely standard. Basically everyone gets a smaller slice of the input as we increase the number of nodes. So there's no complicated data shuffling or anything like that.
And what is the cost to move the data in the GPU memory?
I mean, these are extremely well optimized. So I would say it depends a lot on the model, but I would say the utilization, the raw utilization of a GPU at the specific batch sizes I was working at here was above 90%, probably around 95%. So I would say there's very little in terms of data movement overheads that we're discussing. And I'm kind of bulking these into the computation overhead. Okay. All right. Good. All right. Good. So all right. So what is the actual algorithm that we're running here? So basically, in fact, this was kind of a good introduction to this. So basically, you can assume that we have a bunch of GPUs here, or nodes, and then each one gets a consistent slice of the data, like let's say a quarter of those 1.3 million images, and then we will perform a lot of iterations, where in each iteration we're going to compute an update. Basically, we're going to look at the data and then obtain a prediction from the algorithm. And then based on the fact that our prediction is correct or not, we will compute an update of the weights of the network in order to make the prediction next time to make the prediction correct. Okay, so this would be the gradient or the update. And then we're supposed to average these updates. We'll go over the structure of this algorithm in a lot of detail later. And then we're going to sort of update the model based on the average of the updates. And then we're going to do this literally millions of times if you want to train a highly accurate model. And once we've done this, let's say 1 million times, we have obtained the model that can distinguish cats from dogs. So this is kind of the magic of deep learning. But this is pretty much what happens. I mean, I'm not making anything up. Any questions so far on this? Okay, so basically we have the standard data parallel. We're just splitting the data across all of the nodes we have. Okay, so let's see what happens as we use larger and larger models, because the model I was trying to train on the supercomputer was admittedly pretty large. So the update gets larger because we have more parameters to update. So if you remember the picture on the previous slide, the update used to be smaller. Okay, and then we actually also the averaging part gets larger because we have more stuff to send, right? We have more parameters to update. And then we need to update the model. This is pretty much the same. And then we sort of do things over and over. But what we notice is that what I notice is that the more nodes you use, essentially, I mean, the update part is kind of constant. However, the averaging part starts really ballooning. And this is kind of the red part that you've seen on the previous slide, whereas the other parts kind of stay pretty much constant. Okay? So this is kind of the intuition that your colleague voiced earlier, which is that as we increase the number of nodes and we increase the model size, this part here kind of overwhelms the useful part, which is the computation. Okay? So the idea that we're going to look at today, one of the ideas we're going to look at today is basically adding some kind of compression here, which will allow us to exchange a much smaller amount of information at every step. And then we're going to decompress it on the other end, update the parameters, and do this over and over again. Okay, so this is kind of one approach, one kind of distributed computing approach towards doing this. the other issue in practice is that we're not only dealing with the fact that these nodes are like have a lot of stuff to send. The other problem is that some of these nodes might get, let's say, like more examples, or they might actually get hiccups in their sort of computation. Basically, maybe a node sort of has slightly slower frequency or something like that. So then for instance, it could be that certain nodes take longer to compute but less to communicate. Certain nodes take longer to communicate but less to compute, and so on. So basically, we also can have to deal with the fact that in a system with 1,000 GPUs, not all of them will run precisely in lockstep. So basically, we also have to deal with imbalance and asynchrony, and this is also something we will need to think about. And the point is, in such settings, we're going to be wasting computation time because we're forcing everyone to basically synchronize over here, which means that we might have to wait for the slowest node in the system to make progress at every one of a million steps that we need for training. Okay, so that's kind of the second issue that we're going to need to deal with today. So basically, today's lecture is going to be about efficient distributed computing methods in machine learning. And we're going to talk a bit about communication compression, also about reducing synchronization, or introducing asynchrony into the iterations. And then we're going to see that these optimizations do not come for free. So basically, we're going to be able to push in more compression or more asynchrony at the cost of decreased convergence. And what this means is that in practice, you're going to have to tune your sort of algorithm better towards the system that you're actually running it on. Okay, and then this is pretty much a lot of nice, hopefully nice motivation for going over a bunch of math, which will happen in the second part of this lecture and to some extent in the first part of the next lecture as well. Okay, so all right, so any questions so far on this material? All right, so good. So let's first try to go over the very basics of optimization that we're gonna look at these days, and then like today, and then I'm also going to start like scribbling some stuff so you can sort of work out the definitions and some of the convergence properties. Okay, so I mean, from the point of view of distributed computing 101, which is why I put this very nice book here. We're dealing with a synchronous message passing system in a fully connected topology. So this is literally, like if you go to the Atiyah and Welch book or to the Lynch book, this is literally the first thing you see in the first chapter. So we're not doing anything extremely complicated in terms of distributed computing, but our trade-offs are a bit different, okay? So basically, we have, let's say, two nodes, and each node, instead of getting an input, let's say a 0 and 1, and trying to decide on the 0 and the 1, which is kind of the problem we really love in distributed computing, this is actually kind of a weirder problem. So they actually each get a dataset partition, which I'm going to call DI. Basically, they get a distribution of inputs, okay? Each one of them has some samples. You can imagine that this guy has the dogs, and this guy has the cats, okay? And now, they get a loss function, which says, okay, each one of them, let's say, has a model, and they can measure how well the model does on the dogs and on the cats, right? And this is measured by a loss function, right? Your loss is larger if you're not doing very well. So basically, we can measure how well a model X does on a specific sample E, okay? And then basically, our loss function at the first node will be f1 of X, which is the expected, or let's say average loss over samples from its own data distribution. And this would be the same for node 2. And what we want is we want a model that does well both on cats and on dogs. Therefore, we want a model which minimizes the average over these two functions, okay? And the interesting thing is that, I mean, notice that if we only wanted a model that does well on dogs or on cats, we wouldn't need to communicate at all, right? We just take the GPU, train on the cats, and we're done. However, the fact that we want to minimize like a joint loss means that we need to, like, bits need to cross this wire because of this, right? And this induces communication complexity, and this essentially forces us to sort of spend some time thinking about how this communication is done and how many bits we actually need over the wire and so on, okay? Good. So now let's look a bit deeper into how the algorithm works. So we have that each node maintains a copy or of an estimate x of the model parameter. So let's say, and we're going to iterate over this over time. So let's say this is xt. So then we have a bunch of iterations until we converge. Okay. So what happens is that each node will sample an example ei uniformly at random, and then computes the update, which I'm going to call the gradient here. So this is the gradient at time t by node I, which is basically an update with respect to how well you've done over ei at time t. And then they exchange these gradients, they average the updates, and then they update the model via the average update at this point. Okay. All right, so then they have obtained xt plus 1, and then they do this over and over again. Does this make sense? All right, good. So then notice that if each one of them has a model of size d, or essentially d floating point numbers, then they will need to exchange, each one will need to send and receive 32 number bits times d bits per iteration. Okay? And our problem in some sense in my previous example was that 32 times d was actually too large. Okay? Good. So let's actually get some intuition as to why this is useful, or why do we want to do things this way. So let's assume that we want to solve a trivial problem. Let's assume that each one of them has one-dimensional points, and they want to solve mean estimation. So they essentially, imagine the points are on a line, but they're kind of randomly split. And we want to find the mean of all of the points on this line. So then the algorithm becomes something that's very natural. So basically what happens is that in every iteration, each node will select a point on the line, see how well its current estimate of the average over points is doing, and the gradient will be literally the point minus the estimate, right? Because that's kind of how, I mean, basically your ideal estimate would be literally perfect on average, right? And then you will average, basically what happens is that they average their 2 points in order to obtain the gradient. So instead of taking, like, notice that instead of doing their gradient with respect to a single point, if they average, they take their sort of, they check their estimation against 2 points, and then update their estimates via this iteration, okay? So, I mean, why is parallelization useful in this case? Before, if we only had a single node, in a single iteration, we would see a single point. Now, in the same amount of time, we essentially see 2 points. Therefore, we're going to converge faster towards the mean over all of these points because we see twice the number of samples per iteration, right? Or at least that's what the theory is. Okay? So we do again the exchange and so on. So basically, the HTT algorithm by itself just remains the same, except that we see more samples per iteration. And the funny thing is that exactly the same algorithm is being run on complex neural networks which do like super fancy losses, right? I just gave you kind of the most basic example. And then the question is, why does averaging or parallelism help in this case? So, I mean, then does anyone have any intuition? Yeah?
You emulate a situation when you process all your data on one node?
Yes, so we're kind of trying to simulate, we're kind of simulating the case in which all of the data is processed by a single node, except that we're paying a single unit of time for seeing many more samples, right? That's kind of the intuition. We're trying to fake the fact that, I mean, our single node can only process so many samples in a single step. We're trying to multiply that out by our number of nodes while paying as little as possible for the communication. Okay, so basically the intuition here would be that we believe that our algorithm is always going to be better if it sees 2 samples per iteration or rather than a single one. And this is, I mean, essentially this reduces the variance of our sampling at every step. Okay, so to illustrate this, we're actually going to go into this a bit in a bit more detail later. So what we're trying to minimize is literally a differentiable function f with sort of over Rd, so basically over a d-dimensional space with values in R. So this is our loss, okay? And then the classic SGD iteration literally looks like this: xt plus 1 equals xt minus learning rate times gradient, where we know that the expected value over samples of this gradient is literally the full gradient of the function. And if you're kind of uncomfortable with this notation, don't worry, we're actually going to go over it in a bit more detail later. And then imagine that our variance, sort of the variance of this stochastic gradient. Notice this is a gradient that it's kind of a random variable, right? We're selecting a sample, measuring the performance of our model on that random sample, and we're kind of thinking, okay, if we are going to update our model to go sort of to do better on this sample, it should actually do better on the whole sample set. And we do this kind of iteratively. And notice that if we denote by sigma squared the variance of our stochastic gradient relative to the full gradient, okay, this is how far we are from the mean, then we will actually, this is kind of the standard SGD theory, which we will revisit in the second part of this lecture. It says that if our function f, let's say, is convex and smooth, so it's kind of differentiable, and we start at a radius or distance r square from the original one, so our x0, our initial iterate, is r square away from the optimum, then we only need to run SGD for t is order initial radius times 2 times the variance over epsilon square to get within epsilon of an optimizer, like a minimizer of this loss function. Okay? So let's forget about, let's sort of forget about the exact definition of regret here. Notice that all that matters with respect to the problem definition is how far you started from the original minimizer, how close you want to get to it, and then what the variance of your gradient is. Okay? And what happens when we select 2 samples instead of 1? We're actually dividing our variance by 2. If we're selecting p samples per iteration instead of 1, we're dividing our variance by p. Okay? So this is literally what happens. So if we're averaging our gradient estimator over p samples at the step, then the variance, this is basic variance math, we just we're dividing this by p, and therefore the number of steps we will need to converge within epsilon, it immediately becomes sort of smaller by p. Okay, so that's kind of what happens. And then what we're saying is, okay, we want lower variance because this will allow us to converge faster, but we have to pay the cost of averaging at every step. And if we assume that this cost is 0, then we actually have gained sort of speed up of order p. However, in practice, we might actually not always get this perfect speed up. Okay? Any questions about this? Are you sure? I would have some questions about it. All right, we'll go over this once more a bit slower. But basically, let me take a step back first and look at kind of what the abstract problem here is. So notice we have these 2 nodes. They have their dataset partitions, and we're trying to optimize over this. We want to find a joint minimizer of their loss functions, and this means we need to send bits over, we need to send bits over the wire, or we need to take additional iterations and so on. So this is going to be the kind of abstract theoretical problem we're going to look at today. And I'll try to show you a couple of applications that we'll go over in a bit more detail in sort of after the break. So one would be this idea that we want to reduce the number of bits that cross the wire in order for us to converge. And one approach to do this is what's called gradient quantization, which is kind of a standard method for doing this these days. So what does it mean? I recall that a single node needs to send sort of d values to its neighbor in every iteration because they need to average their 2 gradients. Okay? And gradient quantization in this case means that we are just reducing, let's say this is kind of FP, like floating point, like double or single precision. So basically, let's say this is 32 bits per color here to send all of the colors to the other person. what we're going to say is that maybe we actually don't need so many colors. Maybe we don't need to send the full information about every single sort of update in this gradient to the other guy. Maybe we can just do it with fewer colors, because fewer colors will take less bits to encode, and therefore will be easier to communicate. So here's one way to do it. It's kind of historically the first way to do this. So I always try to present it because it's kind of interesting. It's not the simplest nor the best, in fact. But this is kind of how it works. So imagine that kind of the gradient update at the node, which is a vector of d values, would say, okay, this weight has to be updated by this amount, the second weight has to be updated by this amount, and so on. So basically, this gradient vector, we essentially want to compress it by taking the values and not making them sort of FP32 anymore, like real numbers. We would like to compress them into, let's say, their signs. Notice that this is where the name of the method is coming from. It's supposed to be a single bit per sort of location. So either it's kind of positive or negative, okay, where we assume 0 is positive. And then we also send the average over positives and the average over negatives, okay, some kind of scaling information for this vector. And then the quantization function literally says I'm going to replace 0.1 here with the average over positives. So basically here it would be 0.2. Minus 0.3 would get replaced by minus 0.2, which is the average over negatives, and so on. So I go over all of these. So for every component in the gradient, I would only send its sign plus the average over the corresponding the corresponding group, okay, either of positives or negatives, okay. And the key here is that, notice this is a very rough approximation of the original. It basically only roughly shows the direction, the original direction, and certainly the magnitude is very much approximated. So they actually save the quantization error and apply it to the next update, which is something we're going to analyze sort of later today. Okay, so basically, maybe to make sure people are following, let's see how much compression can we actually get out of doing this. So basically, we had, let's say, I don't know, 32. Like we had a vector of size d, and each component had 32 bits to be encoded. Now we're replacing every component by its sign, and we need to send sort of two floats, one for average over positives, one for average over negatives. How many bits do I need for this?
D plus 64. D plus 64.
Yeah, that's exactly right. So basically, I need to send two floats, average over positives, average over negatives, plus d bits. Right? So notice my compression rate is very, very good. So basically, it's almost 32x. If I didn't have these two floats, it would be perfect. However, this doesn't always converge. So this is kind of the first thing, which was kind of done essentially by engineers, but it doesn't always work. Okay, so I'm going to show you a version that's maybe a bit more complicated algorithmically, but it does have convergence guarantees. So basically, we have the same. Imagine we have sort of the same vector, and then we're gonna essentially want to split it into two parts. The magnitude of the vector, which is going to be its L2 norm, so the square root over sum of squares. And then we're gonna, for every location, we're actually going to use 2 bits to encode it. So 2 bits means we can express 4 possible quantization levels or integers to which the value can be assigned. Okay, so let's say our 4 quantization levels are 0, 0.33, 0.66, and 1. Okay, and now let's say so basically notice these I can encode very easily by 0, 1, 2, 3. Okay, so let's say my normalized value is 0.4, which would stand around here. And then every time I want to, the question is which one do I throw this onto? Okay. And turns out doing things deterministically here is kind of wrong. So the ideal thing to do is basically flip a coin, and with probability proportional to this distance, you actually throw it here. And with probability proportional to this distance, you throw it here. So basically, the larger, basically the closer the value is to 1, the more probable I am to throw it to 1, and sort of vice versa. Okay, so that's kind of the idea here. So let me so basically now let's think how many bits do I actually need to express this vector using this sort of representation. So remember, I have the scale, which is a 32-bit floating point number. I have sort of d times sort of 4 d times 1 of 4 quantization levels, and then I need to keep the signs as well. So how many bits do I need for this? Not 5D, because it's 4 quantization levels, it's not 4 bits. It's 3D plus change. Yeah. All right. So basically, this is sort of the formal version of this, where each value becomes the 2 norms times its sign times this random variable here, kind of the outcome of the random variable. And indeed, basically what I will have is v sort of, I need to send the float plus d log s, where s is 4 in our case. This is the number of quantization levels we're using. So basically, we would get around compression ratio about 10x. Okay, here. Yeah.
Previously, you said that the ideal is to do this, but how do you define what is the ideal?
Yeah. So basically, I'm not going to discuss this today, but basically, yeah. But literally, there's essentially. I'll maybe I can cover this on the next slide. But the point is, like, there is a trade-off between the amount of variance you add to in the gradient and the amount of compression that you perform. So basically, and we have a paper with my former postdoc Janne Korhonen, where we show that there is like we prove that for any compression scheme you will have this, and we show that the version of this approach actually hits that trade-off. So basically, there is a lower bound, and for some very careful parameterization of this approach, this is not optimal, but for a version of this approach, you can actually hit the trade-off. Okay, so to be a bit more clear, so what we're doing here is, so this is kind of our quantization function, and notice that the key reason why this looks a bit weird, why we're sort of flipping a coin here, is that we want that in expectation, every quantized value actually equals the actual value. And this happens if you sort of use the probabilities properly. Here, we will have some kind of compression rate, provable compression rate. So basically, the expected number of non-zeros in the quantized vector will be s square, which is sort of the number of quantization levels, plus square root of d plus the square root of the dimension. And then for a specific s and d, you will also have a variance bound with respect to like how much additional variance you're actually throwing into this vector. So basically, this ensures convergence because we still ensure that the sort of a quantized vector is still an estimator, a proper estimator of the gradient. So you're still, on average, you're still going in the right direction. Now, sparsity, this kind of gives you sparsity, so it gives you some degree of compression, okay? Because it says the number of non-zeros in the compressed vector is actually not so large. And then we also, this essentially shows us, remember like on the previous slide, I showed you this trade-off between the variance in the gradient and the number of iterations we have to perform to converge. So basically, this gives us boundary variance implies sort of faster convergence, okay? So in particular, if we choose our parameters properly, you can actually get kind of an optimal, close to optimal variance, sort of compression variance trade-off. Okay, so basically, so I think this actually sort of addresses your point to some extent. So basically, there exists a setting of parameters for which you converge at most 2x slower, such that you only send about 2.8 times d bits per iteration. And we can show that you cannot do better than d per iteration. If you do if you send less than d, or like let's say square root of d bits per iteration, then you will actually need like by however much you cut from D, you'll actually have to pay in the slowdown of your algorithm. Okay, so at least what we show is that practically you converge kind of similarly to the original, but you send 10 times less bits. I'll skip the proof because we will cover this later. And like there have been like this paper has kind of quite a few follow-ups by now, where you can actually reduce this number here. So basically, you can get like closer and closer to a full like a clean factor of D. Okay. Yeah.
What was the D again?
D is the dimension of your vector.
Oh, yes.
Okay. So, all right. So I think I've stressed you enough with equations for a bit. I mean, we're going to get back to equations soon. But basically, I just want to show you that this actually works. Okay. So I'm going to show this to you on some experiments we did kind of a while ago. So we used some standard networks for image classification, and then we essentially trained on, let's say, 2 GPUs up to 16 GPUs, and we used a version of this that's fast to encode and decode per iteration. So this is let's say 4-bit quantization, so S equals 16 quantization levels. Okay, and we just ran this without additional hyperparameter tuning for the model. So basically, remember that we were motivated by this split between communication and computation for my CSCS example, right? So remember that we had 60%, in this case, if we run on 2 nodes, 60% of the time is spent on computation and 40% of the time is spent on communication. Notice that this is much better than the example I showed you because I have 2 nodes, I don't have like 1,000 or 64. Okay, so this is what happens with this network if you train it this way. And what we noticed is that if you compress communication by about 8x, which happens if you go from 32-bit gradients to 4-bit, your sort of degree of, well, like the ratio of communication from like in the entire sort of end-to-end computation goes from 40% to about 5%, which sort of makes sense because it's kind of 4x. It's about 8x, right? And then this means that the computation, which kind of stays almost the same, we're adding a little bit of computation because we have to encode and decode gradients at every step. This gets reduced from the ratio of this gets increased from 60% to 95%. This means that we're using our computation our GPUs much better because they're actually spending most of their time doing computation and not communication. Okay? Good. So then in terms of actual convergence, notice that, I mean, these are the convergence. This is basically how good the network is at recognizing, let's say, among 1,000 different classes. So this is essentially it's test accuracy on an unseen sort of set of images. And notice this is basically going pretty much exactly the same between standard SGD without any compression, SGD with 8-bit compression, or SGD with 4-bit compression. Okay. Notice, like in this example, there is a minor gap between sort of 8-bit and sort of 32-bit and 4-bit are actually about the same, and 8-bit is a tiny bit better, which is kind of a funny phenomenon that I cannot explain. But basically, the quantized version actually is a bit more accurate. Probably there's some kind of noise and regularization happening. All right. So does this make any sense? Any questions? All right. Good. So I'll skip the experiments because I would like to go into, I'll try to go into the sort of theory. I'll still have some time. But basically, the summary of things we've discussed so far is, I mean, I've tried to motivate distributed sort of computing as kind of a key component of machine learning. And we've seen a bit of quantization. We're actually going to look at a different way of reducing the number of bits that are sent, which is going to be sparsification. This is going to be a bit more complicated, but also more interesting. And these techniques can provide a lot of communication reduction. Basically, we've seen that you can reduce, in theory, by about 10x, in practice by about 8x, and basically with sparsification, you can reduce the communication by about 100x. So, which is why in today's systems, communication, sort of the gradient communication is no longer thought of like as a major drawback, but we'll see like right at the end of the series of lectures, we'll actually go back to this problem and see what happens, like what are the challenges when you actually train something of the size of ChatGPT. So you actually still get communication issues, but not on the gradients, but actually on the weights. Okay? Yeah.
Sorry,
Yeah.
I think I lost my attention for a while. So I understand more or less what quantization is.
Yeah.
What's sparsification?
So basically, imagine that we just chose to drop, we chose to drop 99% of values. We just choose to drop them, drop the updates, like 99% of them. And so each node will choose whatever it thinks the most important 1% of updates is, and it's going to communicate them to every other node. So that's going to be, that's a very basic instance of sparsification. Does this make any sense?
So you just send less information.
You send literally less information. Arguably, notice that also in this, like in the case of quantization, we were also kind of selecting based on magnitude in some sense. Like basically whatever, like something that was larger could actually sort of take up more bits than something that was smaller. So it's not sort of, there was some kind of important selection in that case as well. But yeah, so to answer your question, this is one way of doing sparsification. The reason why it's in italics here is that it's not properly defined, but I'll define it properly actually sort of at the beginning of like the second session.
You're going to talk about this.
Yes, we're going to discuss, we're even going to prove convergence bounds for it, assuming I have the time.
I'm sorry, can we go back to this Amazon testing?
Yes, sure.
I think I need something there.
Yeah.
This one, yeah. So you compare the results of your quantization techniques with different parameters.
Yeah, so basically this is essentially, this would show you like how much time does it take to do a pass over the data. So this is like 1.2 hours is without any compression, and 0.8 hours is with compression. Okay, so we've gained about, I don't know, 30% or something like that.
In terms of accuracy.
So this is what I was discussing here. So we're actually not dropping any accuracy in this case. So what I was discussing was, if we're looking at, let's say we're looking at top 1 accuracy, which is basically how, we always, like the network essentially gives you an output probability distribution over classes, and it's kind of up to you how you interpret that. But if we take kind of the top class in terms of probability, let's say dog, and then I say, okay, the network thinks that this sample is a dog. So basically this would be top 1 accuracy, and we compare it against standard SGD without any compression versus 8-bit SGD, which would be this green line, versus 4-bit QSGD, which would be the blue line, which is overlapping the red one. So what we notice here is that basically the 4-bit and 32-bit are doing exactly the same, whereas the 8-bit compressed version is doing slightly better. So what we obtain, not only we have preserved the accuracy of the model, but we've actually improved it by a tiny, like let's say less than 1%, by doing gradient quantization. Does this make any sense?
I didn't understand the curve from the top, like the.
So this is as we're seeing. So basically, you mean this one?
No, the SGD.
These are two metrics. This is basically this is top 1. This top 1 is this whole graph, and this is top 5, which is also another metric where we essentially say if the network hits, like if one of the top 5 answers by the network is the correct one, we give it credit for the correct one. But we're doing this exactly the same across these two. I put both of them because both of them are standard in some sense. Yeah. Does that answer your question? Yes.
Does it include only quantization or also sparsification?
No, this is just quantization. I haven't discussed sparsification at all. Yeah. Any other questions? Yes?
So you mentioned previously that some compression protocols converge and some others do not converge.
Yeah.
Is there a set of properties that if the protocol ensures these properties,
Yeah.
then it converges?
Yeah. So I will give you an example of this specifically for sparsification in the second part. Yes. So basically, these literally are theorems. So basically, you say, okay, under this set of assumptions, like the function needs to be convex and smooth and whatever, then I prove to you that the algorithm will converge within this many iterations if you want to get towards epsilon. So they will look exactly the same as this, but with more preconditions. So basically, you might get some additional factors here which depend on the compression or something like that. Yeah.
So just to understand, maybe I'm jumping ahead, but this lecture is about basically very simple communication pattern. Like
Yeah.
Everybody talks to everybody.
Yeah.
For averaging their
Mhm.
outcomes. But most of it is about reducing the size of messages.
Yes, I mean, there is a second part of the lecture, which I hope I can get to, which is about asynchrony. So basically, this was actually what I was going to talk about next.
Okay, I'm not going to slow you down.
No. I mean, I'm not looking to go faster, but this was literally what I was going to discuss next. So far we've discussed like a networked setting where they, as Petra just said, they are communicating by sending messages to each other. So this was the first chapter of the distributed algorithms book, right? So now we go to the second chapter, and then we look at shared memory. So because people do solve stochastic gradient descent also in shared memory, like if you want to run regression on your laptop or stuff like that. So basically, what does this mean? Well, we have exactly the same setup in terms of data. So each thread now will get a partition of the data. And now their model is shared, right? So the model, like you can imagine that each one of these is a register. And the vector of d values is a set of registers, right? So you can imagine like a snapshot object if you want to be fancy or something like that. But basically, so what happens is that in each iteration, like let's imagine that these iterations are completely asynchronous. We have a bunch of threads. In each iteration, a thread grabs an example from their dataset partition and now wants to apply this update over the general vector. Okay, what does this mean? It means that at a sort of time t plus 1, what it will do is, in order to obtain the sort of variant of the vector at time t plus 1, it needs to compute this gradient. Okay, so in order to compute the gradient, it needs to first collect the current version of the model, compute the gradient with respect to the current sample, which is this, and then it needs to go ahead and update every cell of this vector to sort of match the expected value of xt plus 1. Does that make any sense? All right. So this is why there was a, oh, sorry, I'm going in the wrong direction. This is why there was a lock here. So basically, you can do this. You put a lock on the full thing, and then this magically works, right? If we do a lock, like you do a lock for reading, a lock for writing, this becomes completely sequential, and this should work fine. We agree, right? But this is horrible because basically, I mean, we have gone, like we've thrown away all of our parallelism in order to put the lock here. Okay, so then there is this kind of story in this community which says that there was this group from Stanford which was playing with this, and by mistake a student commented out the lock. Okay, and then they ran exactly the same code, and it converged. And then they started to look for some theory for this, like why does it converge, when does it converge, and so on. And this is a paper that's called Hogwild. This was sort of the original paper that did this. Basically, they managed to prove convergence under the example where, let's say, each thread only touches a small subset of the entries, which is sometimes can be reasonable. So you can just imagine that each thread can only needs to read and write, let's say, 2 entries from this vector. in every iteration, and they managed to prove some bounds for this. But basically, this created, I think the paper has more than 1,000 citations by now, and this created a whole direction of work where people try to understand sort of when and how this asynchronous version of SGD also converges. Okay? So basically, the question that this line of work tries to answer is, does SGD still converge under these types of iterations? Okay? So, I mean, I'll be coming back to this picture. This is kind of trying to split what's happening over time, so you can kind of understand the unrolled version of this, but we're going to come back to this in the second part of the lecture, so maybe I'll skip it for now. All right, but the intuition behind convergence is kind of as follows. So basically, we are trying to optimize a loss function, so we're kind of trying to get here. Our sort of parameter here has high loss, and then over a sequence of kind of random steps, we want to try to get closer and closer to here. Okay, and then what happens if you remember your standard adversarial analysis of, let's say, consensus algorithms in shared memory, what happens is that you have these updates which are created at these points, which are basically, these are literally gradients that need to be applied, but the adversary freezes them in time here and doesn't allow them to be applied. All right, and the adversary's power will be to, let's say, it will enable these to be applied later in order to push us as far as possible from this point, which is where we want to get. Okay, and the adversary's key limitation will be just the maximum amount of delay that it can apply between the point when the gradient was produced and the point when it needs to be applied. Okay, so basically, what the adversary can do is like, oh, it sees we're close to convergence, it will actually push us, let's say here. I mean, technically, this would be sort of up in terms of loss. Okay, so then we will need to take more steps in order to converge to the same point. Okay, so that's kind of the analysis we will need to come up with, but it will be a bit more complicated than this. And I feel like I need to add this because this is kind of the original Hogweld result. So it says, under analytic assumptions, in particular on the number of components that can be written to, then you can actually converge with asynchronous SGD, but at a rate that is theta times slower than the original one. So basically, the adversary gets like a linear power in the delay to sort of slow you down. And it turns out you can actually do a bit better than this. This is not a lower bound. Okay? All right, so this is, I mean, the nice thing, I mean, one thing that I find a bit funny here is that this result has, yes?
So there should be some bound on the number of steps that the adversary can delay, right?
It's n minus 1, right? It's basically, the n is the number of threads. So basically it can delay all but one in some sense. I mean, you'll see, I mean, perhaps we won't go that deep into this, but we can maybe discuss it offline. This is very similar to the types of interval contention type of analysis that we are used to, in fact, yeah.
Tau?
It's the maximum delay. It's basically the maximum sort of delay between the point when the update was generated and the point when it is actually applied. So this would be interval contention, right? This is how many operations can occur between when you started and when you ended. Yeah, a rough measure of interval contention, I guess. Yeah. Of what?
What's the point of this delays? Is it only to solve this problem of that some nodes go faster than the others?
Yeah, yeah.
And is it, I mean, as long as if the data is partitioned somewhat randomly, is this really a problem that some nodes go faster?
I think this. I mean, I think this is a very good point, and I think this is where things went a bit. Practice went a bit differently from theory. So I think this is a very, very good question. So I guess there are two things you might want to question here. So first, like what is the worst thing that the adversary can do? Which is what this theorem was trying to say. Like it was saying, it doesn't diverge, but it converges much, much slower, right? This is what the previous theorem was saying, and this is actually said here. So basically it says, we will be order theta times slower in this case, right? Which is, in the worst case, this could be really, really bad, right? Because you could, like someone could be delayed by a very, very long time, right? So this is a worst case bound, all right? But now someone who's more practically minded, let's say like you, comes and says, well, but I mean, in practice, delays, maybe you miss a few iterations, but this is not such a big issue, right? Because nodes are synchronous, more or less synchronous, and they certainly are not scheduled adversarially. So then you say, okay, but then let's say this is constant. But then this result is still valuable in some senses because it says, if your delays are not too bad, then you should converge at pretty much the same rate, right? Which is what this result is saying, right? So my point is, I think there are kind of two ways to interpret it. One exact way, which is as a worst case lower bound, and one maybe inexact or more practical way, which says, how bad should it be on average? And on average, I'll show you some actual experiments where on average your delay is, I mean, on average, sometimes you don't even see it. Like basically, sometimes they just work exactly the same way. Okay?
But it's order t, not order n multiplied by t.
Order, where is the d here?
The tau.
Yes. Why is it not order n multiplied? I mean, okay, so it's basically because of this. So basically, there is an example. The kind of the worst case lower bound is something like this. Someone generates a gradient at the very beginning, and then you converge. And then that person just gets sort of updated right before you converge. And then you practically, you can build the loss function so that basically it's kind of, you have restarted from scratch in some sense.
The delay is all n, right? It can apply
Like the notice.
all red updates at the very end. So it
Yes.
will take you out by n times t.
But this is multiplicative. The theta is multiplicative here. So basically, you'll have to repeat the same iteration literally theta times. Does that make sense? So literally, you're gonna end up doing everything.
So the theta is tau.
Tau. Yes, you're gonna have to repeat everything tau times, which is kind of what the worst case example is. Yeah, I mean this is also, I mean this is not. Unfortunately, this is not that meaningful because it means there's no parallelism in this case. Like in the worst case, basically since tau can be seen as n, for instance, you can build an example, then basically you don't get any benefit. In the worst case, you don't get any benefit out of parallelism at all. Okay? You can, I mean, much of the work for this is actually to come up with schemes which are able to get benefits out of parallelism provably in the worst case. I will not talk about that too much. Okay. Yes.
One extra question about the previous slide.
Yeah.
Here there is a theorem which says that this rate loss is tight, but can be improved on average. What does this mean, that the rate loss is tight?
It means that there is like an adversarial strategy and a loss function, so that if you look at the SGD convergence rate, for like the clean SGD convergence rate without any asynchrony, you get, I don't know, let's say t, and then with under asynchrony you will get tau times t. So basically it will be tau times worse. We will discuss this a bit later. Yeah. No, sorry. Go ahead.
I thought that this is what you say is determined by the rate that is O of t times O. That's clear. But what is not clear is what the tightness of rate loss.
But my point, this is what. So what I mean is that what this. So basically, this says, okay, in the worst case, you will converge like tau times like a sequential rate, right? And my point is, like, I can give to you, I mean, this is the upper bound. This says the worst case you should be able to get is order tau times t. And then what I'm saying is this is tight because there is actually a strategy which I can instantiate. This is how the adversary does things, which actually gets exactly this rate for one example. Okay, so this is tight. Like basically, this says, okay, there's an analysis which says, I know, you can take at most a day, and there is a strategy which actually takes you exactly a day. Okay. Yeah. All right. Good. So, all right. So basically, this is was my short snippet on asynchronous SGD, and basically this was maybe the example that I wanted to show you. So this is what actually happens on kind of well-behaved examples. So I don't know if you can see this, but basically, this would be the convergence time for one thread, 3 threads, 10 threads. Sorry, this is the convergence rate. So this is number of iterations, number of epochs versus training error. And they are all the same. The reason why you cannot see the difference is that they're literally all the same. So in this case, what this means is that this is taken from this original Hogwall paper. So basically, there is no loss here. There's no kind of accuracy loss in practice because the delays are not so bad. Okay? And this presents the speedups for the same example. So basically, their speedups are pretty much linear in the number of threads. Okay? All right. Good. So all right. So that was kind of my my introduction. So this has been very high level, which also explains all of the questions you've had. So basically, next we'll do the basic theory that's kind of necessary to understand these methods. And then we'll look at sort of SGD convergence with and without compression, and asynchronous sort of SGD as well. Okay? So that's the plan next. And I'll switch to my tablet. So we'll actually do some derivations. But first, if you have more questions, I'm happy to discuss them. No? Oh, yeah.
I have a question about quantization.
Mm-hmm.
It's not easy algorithm. Did you try simple lossless compression algorithm?
Like zip or something like that? Yes, but it does. I mean, they don't work because the problem is the values that you have. I mean, these floating point values, they are literally floating point numbers. Yeah, so the fact. This is the thing. They're not. I mean, they're not the same, right? Because they're kind of produced by a pretty noisy differentiation process. So basically, you can just assume that there. I mean, there are some general directions, but they're noisy. Like literally, they have. I know the 6th digit after the dot is just like completely random. It's literally like by differentiation. And that. I mean, the point is that if you apply zip or something onto that blob of data, your compression is almost nothing because it's kind of random. So the thing that this trick does is that it reduces them to a bounded set of integers, and there you can apply zip-like tricks, and this is what we do in the implementation. Okay. Yeah. Yes. Yeah. This is lossy compression. This is where this variance trade-off comes in. Yes. All right. Good. All right. So let's see how to arrange this. 1 second. By the way. All right. So basically, like let's start with some really basic definitions. So basically, we're trying to optimize functions of d variables over r, and then we're kind of assuming that our functions are differentiable. Yes. Is this better? And smooth. And we'll define what smooth is next. So maybe the first sort of derivation that I want to give you is how do people, so y gradient descent. So how do people arrive at this sort of xt plus 1 equals xt minus alpha times the gradient, okay? So basically, I mean, so does everyone here know what the gradient is? Like, what is the gradient of a function? Don't be afraid. I think if you don't know, the rest is going to be very boring. So please raise your hand. Okay, good. So I will believe that you know what this is. I mean, maybe to make sure you know. Basically, if the function, the gradient of the function is a function also of d variables, right? Notice this was a question from the audience. Okay, so to arrive at the gradient descent, we start from the expansion of the function. So we know that this function is differentiable, so we can, for instance, write out Taylor's formula for the function, right? So in this case, f of x plus delta, so basically the value of f in a neighborhood of any point x, so for any x, we can write, and any small delta, we can write f of x plus delta is approximately f of x plus gradient of f at x transposed times delta plus 1/2 delta transposed the Hessian, which I'm going to draw like this, times delta. Okay, so here plus some third order terms. So for a function of a single variable, I hope everyone remembers sort of this version for a function of a single variable. Can you actually see this? Sort of. I guess this is, the problem is I don't know how to zoom this out, because on my tablet it's already kind of as zoomed out as it can possibly be. Is this okay?
Can you maybe invert
Invert the
the colors?
color. Sure. Let me try to do that, but I think for this I'll have to. All right. Is this better? All right. So we had sorry, my ink is bad. All right. So basically, we have this function with d variables with values in R, and then we're taking f of x plus delta is basically, we know that this is approximately f of x plus gradient of f at x transposed times delta plus half of delta transposed h second order derivative times this plus some third order terms, like third order derivatives that we don't really care about, because we're taking delta so small that we assume that this is going to be 0. Okay, so now like so basically notice this is going to be like a linear approximation to f locally, and this is going to be some kind of quadratic residue, right? This is basically how close the linear version of this is to the original. So basically, imagine that our function f looks like this, okay? And now basically we're saying this part here, let me denote it by phi x of delta. This would be phi x of delta, right? This is a linear function. And then this thing with that, let me call it rho. Basically, this thing over here, which would be rho x of delta, would be some kind of upper bound. This would be some kind of upper bound on how far the function itself, like the function itself should always live within this region, right? Because we're saying this, this should be upper bounded by this, okay? All right, so basically a gradient descent arises from the following observation. Like, what if we optimize phi plus rho with respect to delta. Like, what if we pick the delta, which minimizes the function locally with respect to this approximation? So basically, what we would get here would be that we essentially we want to minimize something like beta. Let's assume that this is going to be upper bounded by some beta times the norm of delta square. So then we want to minimize beta of norm of delta square plus gradient f of x times delta plus f of x. But we want to minimize this with respect to delta. Okay? So if we write this out as a function, let's assume that that basically d is 1. So if we assume that this is a function of a single variable, then we will get that this is the same as b. We want to minimize the function beta times delta square plus the gradient, which would be literally the derivative, df dx at x times delta plus f of x. However, the min of this is delta, it is actually at delta star, which is going to be minus gradient, so minus df dx over times 1 over beta. Okay, so if we actually want to find, like, recall that we are at x and we want to find the direction which minimizes sort of f locally, then we should actually move to x minus this thing here, right? If we want to minimize the function locally with respect to these approximations, we should actually, so if we are at x, we should go to x plus delta star if we want to minimize f. So then the algorithm is going to be, we start at, let's say, x0 is 0, and then for I from 1 to t, we're going to do xt plus 1 equals xt minus 1 over beta times the gradient of x at xt. And this is literally the, like, this whole thing, like this thing here, is literally what we've been looking at for the last hour, right? Good. So yeah, just maybe for the students who've never seen the derivation of gradient descent. Now, basically, what's kind of strange here is that, notice in order to do this, so let's actually do an example. So let's do an example. So mean estimation. Okay, so let's assume that we have, let's say, m points in R2. Okay, so let's assume we have, this is 0, and we have a lot of points. Okay, and we want to find the mean of these points. So what is actually I mean, then if we want to solve this as an optimization problem, we just say, okay, our goal is to find an x which minimizes the following function. 1 over 2m times sum I equals 1 to m of 2 norm of x minus ei, where e1 up to em are my points. Okay? Does this make sense formally? All right, good. So now, so let's assume that you don't know how to sum the points and average them manually, because this is not the point of this exercise. So, I mean, clearly, like, does anyone kind of know how to solve this problem in this room? What would be a solution to this problem? Let's assume our dimension is 1. What would be a solution to the problem when if these points are on a line? Yes? Yes. Thank you. Thank you very much. All right.
I think that for the arithmetic mean it should be square.
Yeah. This is why I reduced it to the to the 1D version. So in the 1D version, you should take the mean, right? Yeah. So the 2D version, yes, you have to be a bit careful. The distance. I mean, this is actually the proper distance in the multidimensional case. Good. But the reason why we're all here, at least for the next 9 minutes, is we want to learn about gradient descent. So how would you solve this via gradient descent? Like, how would you use a cannon to kill a fly? All right. So basically, I mean, we would need to compute the gradient, right? So what is the gradient of fi, where I is a data point ei? What is the gradient of this function? Let's say, sorry, this is squared here, just to simplify our lives. What is the gradient of this function? So yeah. So basically, if we do, like, with respect to a single point, this would be something like norm. So this would be d over d, like, I guess this would be the gradient of x minus ei squared, let's say with a 1 over 2 here, right? So then we literally get, so we get 2xi, which is what you were saying, minus ei, right? So we get 1 over 2 times 2 times xi minus ei, and then the rest sort of falls away because it's constant. So then we get xi minus ei, okay? So notice this has a very intuitive meaning, right? Basically, if you have an estimate xi for the sort of, let's say, this I is not the same. This would be, let's say, this would be, I guess, something like this. This would be x1 minus ei1, and then x2 minus ei2, right? Because this is a vector, right? The gradient has to be a vector. Okay, so basically in this, given if we are building things this way, then this would be x minus ei, and these are vectors, right? So this means we have an estimate for x, and we see a new point, and then what we want, if we see a new point, that basically our estimate should go towards the point, right? If all of our points were exactly the same, then basically our mean would have to be exactly at this point. So we should just adopt the point. Does this make sense? All right, good. So good. So basically our full gradient, because notice our function is an average, right? So our full gradient f of x, should actually be 1 over 2m times sum I equals 1 to m of basically x minus ei, right? This is summed over all of the points. Okay? But notice that this, we can split this into two parts. Right? So this would be 1 over 2 times x minus sum I equals 1 to m of ei. Right? I just split the sum over here. We have the sum, and I split it into two things. Okay? Good. All right. So, all right. So then let's say, I mean, what is our algorithm for gradient descent? So we remember, I mean, our algorithm, we kind of wrote it here, right? Yes. Very good. Thank you very much. 1 over m. That's correct. So basically, my xt plus 1 equals xt minus learning rate times xt. So this would be 1 over 2 times xt minus 1 over m sum I equals 1 to m of ei. Right? This would be my update. Right? So now let's assume that I actually take alpha to be equal to, just to check what's going to happen. Then this is going to be then my, so after one iteration, basically, sorry, I have a mistake here. There is no 2 in the gradient because it was already 1/2. So basically, this is going to be my iteration. So then xt plus 1 equals xt minus alpha times this. But then if I take alpha to be 1, then I get that xt plus 1 is going to be equal xt minus xt plus 1 over m times sum I equal 1 to m of ei. So what is this? These disappear. So we have 1 over m times sum equal 1 to m ei. So we basically rederived your colleague's algorithm in a very complicated but somewhat meaningless way. Right? Basically what this says is that if you're using gradient descent and you pick your learning rate correctly, in this case 1, to kind of match what your function is, notice we actually have to we can take alpha equal 1 here because our function is an actual quadratic function. So basically, you remember our sort of estimation here is not an over or underestimation. This is actually an exact, like our function literally stops here. There's no third order term. So basically, if our function is a quadratic, then we can take alpha equal 1, like beta equal 1, so basically alpha equal 1 in our iteration, and we will converge in a single iteration of gradient descent. Does this make sense? Okay, so basically it does, I mean, the point of this exercise was to show that gradient descent is in some sense like a meaningful algorithm. And it can allow us to optimize much more complex functions than our linear regression here. But the point is, like, if we parameterize it correctly, it will allow us to converge sort of perfectly, right? So we don't need to do like, we don't need to actually understand what our problem is and sort of solve it via heuristics. Okay, so maybe the last thing that I want to cover briefly is what happens in stochastic gradient descent. So basically, what is the difference between what I've done here and the stochastic case? Alex, maybe. Yes, so in the stochastic case, what we're doing is basically we start again from x0 equals 0, and then for I equal, let's say for t equal 1 to t, we pick example ei, right? And then we say xt plus 1 equals xt minus the gradient of the function at point I with respect to xt. But notice, like, I'll put this in red. Basically, notice that this is the gradient of the function with respect to a single sample, as opposed to taking the mean over all samples. So now, let's try to see how this changes our iteration in this case. So basically, now we get, so for our mean estimation, what do we get? We get gradient fi of xt. Do you remember what this was? So this is literally, this is going to be xt minus ei as vectors, right? So then my xt plus 1 is going to be equal, let's put a learning rate here. So equals xt minus alpha times xt minus ei. Okay? So now notice that if I take alpha equals 1, what happens? Basically, I will always adopt the point that I see, which is obviously not a great idea because I'm not learning anything over time. But now, let me put alpha t, so I'll make alpha time dependent, and I'll put it as 1 over t. So what actually happens? Xt plus 1 is going to be xt minus 1 over t xt plus ei over t, right? Okay, so it's going to be xt times t minus 1 over t plus ei over t, right? Good. So I'll stop in a minute. So basically, notice here, so I can prove the following by induction. Xt is going to be sum of like tau equal 1 to t minus 1 of ei over t minus 1. So basically, I can prove by induction that xt is actually the average over all of the points that I've seen so far. Okay? So then if I replace it, which is certainly true for the first point. So then if I replace this into here, then I'll get that xt plus 1 equals what? It's going to be 1 over t minus 1 times t minus 1 over t plus ei over t, which is, this sum. So this goes away. So I get that this is going to be the full average, t equal 1, theta equal 1 to t of ei over t, right? So if I take an adaptive learning rate, which is this one here, I'll get that my estimate after t plus 1 points is going to be literally the average over all of the points that I've seen, right? And this is a mean estimation problem. So this is kind of the best thing that I could achieve after having seen t points, or t plus 1 points in this case. Does this make any sense? So my point is that both of the stochastic case and the deterministic case can be mapped onto very natural algorithms for specific problems, but they do this completely generally. They do this without us kind of knowing it. All you need to do is tune the learning rate and they will kind of do the right thing. So I've done the example for mean estimation via gradient descent and mean estimation with via stochastic. All right, good. So thank you for your attention so far.